How are you? Good. All right. This lecture could sink or float. So good last one. I don't know. Do you guys have any questions about sinking and floating and density? Anything come up since Monday? Because I'm sure you stay awake at night wondering about these things, right? You do, don't you?
I have a question about the superhero.
The superhero paper, sure.
So you just have to say what the first part says to say what their superpower is.
Yeah.
And then the second part, you're not asking for the introductory paragraph?
No. This first thing is just what's your power?
Okay.
And what's the fundamental physics principle that's going to be involved?
Okay. Do we have to explain?
You don't have to write anything. There's no introductory or a draft of anything. And then some of your sources.
Do we have to explain? We don't have to explain
how
it violates.
You don't have to explain anything at this point. I just want to know that you recognize a fundamental physics principle.
Okay.
And what's your power going to be? Because sometimes I see those two and go, How are you going to do that? And I might contact you. How long does the paper have to be?
700 to 1,000.
700 to 1,000 words. I do that because I honestly don't feel people explain enough that they need to in less than 700. And as much as some people want to go over 1,000, well, two reasons. I'll be blunt. I have this many to read. And hone it in. That way you just don't go off on forever on something.
Those are strict.
They are.
Limits.
Those are strict limits.
Okay. And how many sources?
There's not a limit of your sources. So some go, so I can get away with one? Technically, yes. Practically, probably not. Basically, your sources are, if you didn't already know this, something you're writing or explaining, then you should cite it. It's that easy. It's not hard. And so if you have one source that gives you all the information you need, so be it. But I do, as listed in the rubric and the grading criteria, for your works cited, though, you need to list them all at the end and then cite them in the paper. So if you're explaining a specific physics principle here that you didn't know before then you do a little subscript or a number or something that refers back to which source you're using. And your sources should be specific enough so I can go right to that same place you were at. If it's a book, a specific page. If it's an online website, where in that website? If you interviewed someone, well, obviously I don't know what there, but maybe a certain question. But they should be specific. Other people ask, okay, what format do we need to use? I don't care. That always bugged me in English because, well, this person wanted to use this style, and this person wanted to use this style, and this person wanted to use this style. As long as all the information's there and I can find it, I'm happy. And you don't have to be that specific at this point. You will in your final draft. At this point, you can just give like the URL or the name of the book. And you can use our textbook. You can use me. If you have a scientist friend, journal articles. I mean, you can use anything as works cited as long as you cite it. There was a few hands, but maybe I answered them in the process. Yes? Yeah, I do. Within a textbook, so I would need the edition and the page, yes. So I know right where you got your info. Yeah, too many people just say, oh yeah, Paul Hewitt's Conceptual Physics. Well, he's on his 12th edition, and they're big books, so yeah. Anything else? Go this way. All right. Well, we introduced pressure and density last time. We'll continue with that. Here's a block of wood. see, its mass is, I wrote it down on here somewhere. There it is. 1.170 kilograms. All right, and the area of this surface, that area is 0.018 square meters. So when I rest this area on the table, what's the pressure it exerts on the table? Can you calculate it? Do so. What's the pressure that this block is exerting on the table? There's our guide to thinking. What's the force going to be? So its mass is that. Multiplied by 10, we get, we'll just approximate, that's about 12, right? Over the area, 0.018. So whatever the heck that comes out to be. 600-ish? 650? And the units of pressure are newtons per meter. It's a force measured in newtons. Oh. Meter squared. And that's common enough, it's named after Blaise Pascal. The unit of Pascal is the standard unit for pressure. So the pressure this side exerts on the table is 650 pascals. Yes?
So when using mass as force, you always have to
Mass is mass. It's not force. Mass is being accelerated are forces. So yes, you'll, in this case, that's why we had to do that. That's the force that this exerts over that area. In this case, it's its weight. The force it's exerting is its weight. I could push with a certain force over an area, and that would be likewise. But yeah, remember that mass is not the same thing as force. All right. What's different now? Yeah, so what else happens? That's right, more pressure. You can kind of already see just roughly the size of this square compared to this side. What's the ratio approximately? Yeah, this is about half the area of that. So what's the pressure do? It doubles. If you cut this in half, that goes up by a factor of 2 for the same weight. So it is. So yeah, you can change the pressure from this to that. Again, it's like stepping on you with my shoes versus high heels. It's the same weight. You just can exert it over a different pressure. Does that make sense? Just to remind us of what pressure is. Density was mass over volume. So that's in kilograms per cubic meter. And I had some examples for you. They're in the book too, but to give you an idea. Air is, in those units, 1.2 kilograms per cubic meter. Helium, 0.18. Water, 1,000. So it's way more dense than those gases, which you probably could have guessed. What do you think ice is? More or less than water? That's right. And it is 919 on average. Seawater. What do you think is different about seawater? More dense? Why? Yeah, the salt content in it. That's about 1,025 kilograms per cubic meter. So if you mix salt water and fresh water, which one floats? The fresh water, yeah. All right, if we have that the pressure is force over area, so the weight of something over area, with fluids, it's hard to deal with all those little particles. Same with gases. There's a whole lot of little point particles in there. I don't want to add up all their masses. This is where density can have some power. Density is mass times volume, or over volume. So you can represent the mass in terms of the density. You can say what the total mass of all of these little particles is instead of adding them all up or counting them. It's just its density times the volume. Do you see that? So just as an exercise, I'm going to put that in right here. That's the mass. So I haven't changed this formula. I'm just writing it in terms of density. If you have the volume of something, remember your geometry? How do you find the volume of that? Length times width times height. Yeah, that would work better if it was a kind of like that. The length times the width gets us this area, right? And then we multiply that by the height. So you can do the same thing here, that area. It just won't be length times width. It's pi r squared times the height. So I'm going to do that also. Whoops. Do it, Adam. You see that the areas will cancel. And we can now, the whole reason I did that, we can consider the pressure of a fluid. It's the density times gravity, and I usually just use a little h. There's another guide to our thinking. That's still pressure. It's force over an area. We're just representing it in terms of density. What this tells us is that the pressure is depth dependent. So let's talk about that conceptually now. The pressure doesn't care how much of a fluid, a liquid or a gas you have. It just cares how much is above you or how deep you are into it. You know, if you go diving, it's like how far down you are in the water. But in the air, we got air above us. That's the next chapter. So it's, what's the height of the column of air above us? How much air is above us? It's like we're down that far. That would be h. Going to the water to here, that's h. Hey, given that, let's do this one. This is called a Marriott's Flask. I got 3 holes here. I'm going to unplug them all. What do you expect to happen? Water shoots out. How? Will they all shoot out the same? Why? The height's different. How do you think the pressure compares here compared to here? Yeah, there's more liquid above it. So that's your H. You want to know the pressure down here? You now know how to find it. It's the force over the area. We just made it easier, though, for liquids. So we could take this mass of water above this spot, right? We could weigh that, and that's its weight, its force, over this area, and we'd get the pressure exerted right here due to this column of water. Or we can take the density of water, 1,000, times gravity, 10, times that height in meters. I don't know what it is. 0.2, maybe a fifth of a meter. And you would know the pressure in pascals of the water there. And yeah, you can see that that pressure would be less than this pressure. But conceptually, I hope it makes sense. You got more stuff above you pushing down on you, so it's going to have a greater pressure down here. So if the pressure is greater down here, it's going to make the water shoot out faster and thus go farther. Let's see. Can't do them all at the same time, but close enough. There you go. You can see it shooting out a lot faster there, can't you? And as this column of water decreases, because we lose water, see how the pressure decreases? Because there's not as much above it. So it shoots out less and less and less. There we go. Another way to look at that. This is called Pascal's Vases, named after Pascal. I'm going to pour some blue water in this vase. And then I'm going to open a valve so that it can flow through the bottom. Open this valve and it can go into here. And then it's closed over here. This tube is open to these, so the water may get pushed up these, but it's going uphill, so it might not. How do you think this thing will fill up? Why would they all go the same height? They're different shapes. Why do you think they'd go the same height? I heard something over there. Say it out louder. Same pressure? Well, let's see. If they were all the same height, then they'd all be at the same pressure down here, right? So they might be different in the rates they fill up. This one probably faster. Now this one can hold the most water. This one next. This one next, and this one the least because it's skinnier. Will that affect anything? This one will have a lot more water, so there'll be a lot more total water above the point down here. Would that still make them go to the same height? I hope you're at least mentally trying to go with this, because if you're just sitting there going, that's nice, just do it, then you won't learn this as well and might not recall it as much on the test. But that's why I do these pauses, not to annoy you. All right, let's do it. Open the valve. We know there's a pressure down here. And there they go. And about at the same rate. And sure enough, they're all the same height now. This one might be hard to see, but maybe against my shirt, darker or lighter background there, you could see it. So they did all go to the same height. And that is to emphasize that it's depth dependent, not volume dependent. This holds a whole lot more water. So this, if we weigh this water, it'll weigh more. But just look at the opening down here. What's above that? It's just like a column of water. It's just the column that's above it. The column. It just matters how the difference in height, period. Since they're all the same difference in height, they all have the same pressure down here. If one of these was higher than the other, let's say this one went up higher, that means there'd be greater pressure here pushing it up. What's causing that pressure? Well, the weight of these guys. So they all balance. You probably heard the statement, water seeks its own level. Maybe. You can use water to level things because it's always finds itself. You know, you tip something, all right, the water's still level. Let's show it a different way with this guy. So this is open to the atmosphere. And we'll open this side to atmosphere. Blow all the water back in to start with. Okay. And we can fill up this tube. What do you notice about the levels? Yeah, they're the same. What if I lower the tube? It's still the same height. Because the height this is above here causes the pressure. But this is the same height difference, same pressure. If one side was under greater pressure than the other, it would push the other side up. Do you agree with that? Let's do that. If I tighten this, so it's sealed inside. Let's start the same. Let's just start up here. Okay, now we'll tighten it. Same height. I'm going to pump air into the bottle. That's going to increase the pressure in here because I'm going to put more mass in the same volume. I'll increase the density of the air in there. That'll increase the pressure on this side. So the greater pressure on this side pushes this up. But what's balanced? Pressure. The pressure that this column of water, what column? From this height to that height. That's the difference, right? This height, column of water creates a certain pressure head down here. That's what's balancing the pressure we just created from compressing the air. You want to know the pressure inside here? Measure this. You know the density of water, you know that height, you know gravity. You know the pressure exerts down here to balance that pressure. This is essentially how a barometer works. Barometers measure pressure. So if the pressure changes, the height of the column adjusts. They make different kinds of barometers, but this was the first kind. So let's decrease the pressure over here. And you can watch the column of water. Goes down. Oh no, a storm front's coming in. The pressure dropped. And you can tell. This is fun too, with this open. You can even twist the thing around and do things funky like. It's still the same height. You can even have it come up first and then back down. It's still the same height. All this is to reinforce in your minds. Pressure is depth dependent. All right, let's see if I can seal this back up without it leaking. Any questions? Yeah.
So, like, if the submarine is like a mile underwater, which direction is the pressure pushing? From the top or from everywhere?
I'm glad you asked. Yeah, if a submarine is underwater, where do you think the fluid is pushing on this? All around. So it pushes here, and it pushes here, and it pushes here, and it pushes here. Now, which part of the submarine's deeper? So how does the pressure compare? Yeah, so I should draw this like this. The pressure down here is a little greater than the pressure up here. Not drawn to scale. But these are at the same depth, so they'd be the same. And they're a little deeper than this one, so a little bigger than that one. You see this net difference, though, in pressure? I bet you know what we call that. You jump in water, what do you feel? Buoyancy, that's where it comes from. I'm going to show an animation on that same thing here. So good insight there with that pressure difference. Because it's depth dependent, things that are deeper have a slightly more greater pressure than those just above it, because there's more water above it. So here's a little animation. No, not at the moment. I may at the end, maybe not. If not, I'll do them next time. So here's an object, and you can see the arrows pushing on it. You can see that the one, let's just go deeper underwater. If I pull that object deeper underwater, now let's change the height of the object to make it more conspicuous. Let's start there. You can see that the force vectors are larger at the bottom than on the side. They use that formula to calculate the lengths of these arrows. And you can see over here it tells you the net buoyant force. You guys know this. You jump in a pool. What would happen if you stood in a pool and measured your weight? You stood on a scale in the water. What would the scale reading be? You know, I weigh about 165 pounds. I step on the scale in air. Let's move both of me and the scale into the water. I jump into a swimming pool, go underwater, and stand on the scale. What's the scale going to read? I'm hearing more lesses than mores. Why would it be more? Just your gut was telling you more? That's fine. Why less? You'd be buoyed up. This buoyant force is a force. So you have your weight down, but you'd have a buoyant force up. So what's your net force? The difference between those two. And that's all that the scale has to support you with. In other words, think of it this way. The water's helping support you. So the scale doesn't have to support you as much. And it'll look like you weigh less on the scale. That difference in weight is the buoyant force. That's how you can measure the buoyant force for something. Weigh it in air, and then weigh it in water. The difference is the buoyant force caused by the water. So that's what this red column on the right's showing. Now what if we go deeper under the water? I'm going to move the object down. How will these arrows change? They'll lengthen, because we go deeper, all those pressures should increase. What will the net buoyant force do? It'll also go up. Let's watch. Let's go deeper. So yep, the blue arrows, more and more pressure on the object because we're deeper. But look at the net buoyant force. Why doesn't the net buoyant force change? The volume of the object's exactly the same. The difference in height from the bottom of the object to the top of the object is the same no matter where you put it in the water. So the difference in pressure from top to bottom is the same. That's what's causing the buoyant force. That difference in pressure from the bottom to the top. You follow me? So yeah, if you're floating underwater, just under the surface, as opposed to a mile under the ground, under the water, you should have the same buoyant force on you. And you hit it. It's because you're the same volume. All right, let's talk more about that volume dependence then. So the buoyant force is your weight in air minus your weight in the fluid. It could be any fluid. This usually water. That's that difference in your weight. It's actually caused by that difference in pressure due to depth. This is Archimedes' principle, as explained in your book. And it says the buoyant force can also be thought of as the weight of the displaced fluid. I'm going to try to show you that. Let's see. So I have a volume here and a volume here. This fits inside this container. So it's a perfect fit. So the volume of this cylinder, I like that. Volume of this is the same as the volume of the empty space. All right, let's hang this and see what they weigh. All right, we have about 6.5 newtons. That's at mass times gravity here. No, this one. I'm going to fill this reservoir up. Uh-oh. Need a little more. To the brim. There we go. It starts overflowing into here. Let's let it overflow. Close enough. All right, empty that. We'll start empty. So you guys know that when I submerge this in the water, water is going to overflow. I'm going to capture that water. This is the water displaced. Archimedes' principle says that if the weight of that displaced water is the buoyant force. Let's verify. What else, though, when I do this, do you think will happen? What will this do when I submerge it? It should decrease, right? Because the buoyant force should also be the weight in air, 6.5 newtons, compared to, well, let's see. All right, here we go. Come on. There. Is it decreasing? Woohoo! So I'm going to try not to get it resting on the bottom. I don't want the platform supporting it, just the water. But I want it all the way underwater. There we go. Am I on the bottom? Yep. A little lower. There we go. Okay, what's the new reading? Now we're floating. We're not touching the bottom. 5. So, what's the buoyant force? The difference. We started at 6.5, and it went to 5. So it's about 1.5 newtons is the buoyant force. That's how much less you weigh. That's how much the water's helping hold you up. The buoyant force is pushing up on you with 1.5 newtons. All right, it displaced this much water. How do you think the volume of this water compares to the volume of the object? Let's find out. I'm going to pour it back in. Let's see if it fits. Boop. There we are, and, well, darn close. And look what it went back to. 6.5 newtons. So the weight of this water was 1.5 newtons added back. So two things to note. When you submerge an object in water, in any fluid, the part that's underwater, that volume, is the exact amount of volume that's displaced. It makes room for it. And the weight of that fluid or water that it displaces is the buoyant force. So buoyant force is volume dependent. Pressure is depth dependent. Remember, it didn't, if you went deeper, the pressure increased. But notice the buoyant force didn't increase on that simulation. As you went deeper, the difference didn't, because the volume of the object didn't change. Watch this. The weight of the displaced fluid. So that's the mass of the displaced fluid times gravity. That's all that water that was displaced, the mass of it times gravity. That's its weight. And the mass we can write as the density of that fluid, the water, times the volume of that displaced fluid. That's your mass. Just writing it in terms of density. G. So that's the buoyant force. There's two ways to get buoyant force. It's the difference in air versus the fluid. Or we can just look at how much of that fluid's displaced. So if we did this in salt water, what would happen to the buoyant force? It would increase. Why? Because, right, the density of salt water is larger. Think of that. If it's more dense, it's going to help support you more. Ships have to worry about that. When they go from fresh water to salt water or back, they change how they float because the buoyant force on it changes because of the density of the water change. And volume. So, I want to write it out. Buoyancy is volume dependent. So, if I give you, you're drowning, right? And I throw you a life preserver. Here you go. You put it on, you know, that's less dense than water. It helps you float. They're usually made out of styrofoam or something. What if I throw you the exact same size and shape life preserver made out of lead? Here you go. This has the same buoyant force. What do you say? You're trying to kill me. Why? Would you sink? Am I lying, though? Yes, you would sink, but I told you it has the same buoyant force. Here.
Because it's volume dependent.
It's volume dependent. Yeah, that can be confusing to some folks. Let's see. Let's grab something here. Yeah, let's do this. Here's a steel ball. It sinks. And here's a plastic ball full of air. It floats. Who's experiencing more buoyant force? Yeah, this is a more complicated question. It's based on the volume of the displaced fluid. So let's look at how they're displacing fluid. Yeah. Very good. The steel ball, even though it sinks, it's displacing its whole volume, where this ball is displacing just the volume that's underwater. That's all the buoyant force this needs to counter its weight. The buoyant force is up on this, balances its weight. That's why it's not going up or down. Are the forces balanced on this? Other than the string. With the string it is. But if I let go of it, you know what happens. It goes down. Its weight is way bigger than the buoyant force. Yes, it has more buoyant force than that. But it needs even more to counter its really big weight. So that's another way to look at sinking and floating. Things float, they go to the top. Whoop! If the buoyant force is bigger than the weight, right, it'll go up. If the weight is more than the buoyant force, it'll sink. Let's make a chart. So you got two ways to look at sinking and floating. If the density of an object is greater than the density of the fluid, what happens? It sinks until it gets to the bottom. So what do we know about the buoyant force compared to its weight? Yeah, it doesn't have enough buoyant force. All right? If the density of the object is less than the density of the fluid, what happens? It floats. Thus, we know, the upward buoyant force must be larger than its weight. That's why it's going up. And if they're equal, what happens over here? It doesn't sink or float. What's it do? It just hovers there at that depth. Right. These two are balanced. We call that neutrally buoyant. You can try it. Take a thin Ziploc bag, fill it completely full of water, no air bubbles, and then put it in a tank of water. The object is water, mostly, and the surrounding fluid is water. They have the same density. You can get it to just float wherever you put it. That's what a submarine can do. Where'd I draw it? They hover. When they're hovering, it's neutrally buoyant. What's that mean? That means the density of the submarine is the exact same density as the surrounding fluid. How does it do that? It's made of steel. It changes the amount of air or water that it takes in. I mean, it's full of air, or we couldn't breathe inside. So that decreases its density overall. You spread it over big, fill it full of air. That would make it want to float. But if you take on some water, it increases your density and you can go down. What if you want to stop going down? Stop taking on water. Then your combined weight of the ship and the air and the water can equal your buoyant force. The volume of the submarine, the amount it displaces, determines its buoyant force. If you want to come back up, get rid of some water. You weigh less. You decrease your density and you go up. So what's a fish's density normally? Same as water, because they're often just floating around. They have a swim bladder. They take on air or give it up to change their density. But when they're just sitting there, they're neutrally buoyant. They're the same density as the surrounding water. Otherwise, they'd sink or float. You can do it. Have you ever been jealous of those people that could go in the swimming pool, dive down, and just sit there at the bottom of the... How do they do that? Most people just float right back up to the top. You have to fight to stay down. Yeah, blow out some of your air. That decreases your density. You actually take up less volume because your lungs collapse. So you're displacing less water. The buoyant force decreases on you, and you can sit at the bottom. Now, while I have this out front, remaining time, we won't do clickers. Here's a puzzle. These are all wood blocks. Does wood sink or float? Depends. Most wood? Notice the whole volume doesn't go underneath. If the whole volume's underneath, I displace more water. The buoyant force is larger now, right? It's larger than its weight, and it makes it accelerate up. Until it displaces just enough water to balance its weight. Here's one with a big hole. What do you think it'll do? Yep, it floats. They're the same density. They're both wood. All right, what if lots of holes? It's still wood. It floats. So if, for those of you that are confused, because I'm sure some of you are, if you're in a boat, that spreads the wood out and you contain some air in there. That's how, your steel ship can float. What if you poke a hole in the bottom of the boat? Do you sink now or float? You sink. Why? You fill with water, which increases the mass, which increases its overall density, and it sinks. These aren't increasing the mass of the block. It's not holding any water. So it's still just wood. If I had a bottle, and it could fill up with water because of the hole, then absolutely it would increase its weight and its density and thus sink. Now what will happen, these two beakers are balanced. See, they teeter. They have the same amount of water in each side, roughly. What will happen if I drop this ball in this side? Which one? Will they be equal? You probably guessed that one. But the water's holding the ball up. Why does the scale go down? Yeah, you can look at it. It's both ways. All right, what if I hold the ball? I'm supporting the ball. So I'm going to do this, but with it in the water. What will happen? Now it'll stay the same? No? I'm going to hold it in the water. But I'm supporting it. What else is supporting it? The water. Remember, it weighs less in water? The scale would go down. I don't have to hold it up with as much force because the water's helping. If the water's pushing up on the ball, what's the ball doing on the water? And that makes it go down. Newton's third law. And that's whether it wants to sink or float. I can hold it there. As long as some of it's displacing water by being submerged, there's a buoyant force on it. I think that's good. You got any last minute questions? All right. Oh, yes. No, I said your sources for your superhero paper can be anything, just as long as you cite it.